Every atom in your body has a nucleus. Inside that nucleus are protons and neutrons, and inside those are things that refuse to follow the rules. They carry charges physics said were impossible. They cannot exist alone, and they generate almost all your weight without having much mass themselves. We will go inside a proton, survive the energy string that creates new matter from nothing, and face the million-dollar math problem nobody has solved. If you enjoy the ride, subscribe. We are just getting started. Quarks break every rule, and we still do not know why. Let's go. Reach out and touch something solid. A desk, a wall, your own hand. It feels real, dense, permanent. Every bit of that solid feeling is a lie. The atoms that make up your hand are almost entirely empty space. If you took one atom and blew it up to the size of a football stadium, the nucleus at the center would be the size of a marble. Everything else around it would be air, just open, hollow nothing. And inside that marble, things even stranger are happening. Scientists call them quarks. They are the building blocks hiding inside every proton and neutron in every atom you have ever touched. And they do not behave like anything else in physics. They break rules that physicists spent centuries building. They ignore boundaries that every other particle respects. Here is what makes that personal. You weigh whatever you weigh, maybe 140 pounds, maybe 180. Whatever the number is, almost all of that weight does not come from solid matter. The quarks inside your body are incredibly light. If you weighed 150 pounds, your actual quarks would weigh about 1.5 pounds. That is it. The rest of your weight, the other 99%, comes from energy, moving, churning, invisible energy that binds quarks together so tightly it creates the feeling of mass. You are mostly energy walking around in a human shape. That sounds like something from a movie. It is confirmed science. The particles that hold quarks together are called gluons. They have zero mass, and yet the push and pull of those massless gluons generates almost everything you weigh. Your bones, your muscles, your brain, all of it rides on the energy produced by particles that technically weigh nothing at all. Physics has no clean explanation for why this works the way it does. The math describes it, the experiments confirm it. The reason behind it sits in territory that still makes physicists uncomfortable. And quarks themselves make it worse. Every other particle scientists have ever found carries a whole electrical charge. Electrons carry -1, protons carry +1. Clean numbers, simple rules. Quarks ignore all of that. They carry fractional charges, 2/3 positive, 1/3 negative, numbers that had never appeared in particle physics before quarks showed up. When researchers first proposed this in the 1960s, the physics community pushed back hard. Fractional charges seemed absurd. Electric charge came in whole numbers. Everyone knew that. Proposing otherwise felt like proposing that a dollar could only exist as 67 cents. It broke something fundamental about how charge was supposed to work. But two quarks with a charge of +2/3 and one quark with a charge of -1/3 add up to exactly +1, a perfect proton. The math forced the conclusion even when the idea seemed impossible. This is the pattern quarks follow everywhere you look. They break the rule. Then the broken rule turns out to be the only way the universe holds together. You are built from particles that should not exist the way they do, and the force holding them together refuses to let them go. That last part matters more than it sounds, because here is what nobody told you. Quarks have never once been seen alone. In the entire history of science, no single quark has ever been detected in isolation. Pull one out, and the universe fights back in a way that sounds impossible. We will get to why in a moment. First, you need to know how we even figured out quarks existed at all. In 1964, a physicist named Murray Gell-Mann sat down with a problem that had been annoying scientists for years. Particle accelerators were finding new subatomic particles constantly, dozens of them, then hundreds. Every few months, another one. Scientists started calling it the particle zoo, and they meant it as an insult. Physics was supposed to find simplicity underneath complexity. Instead, they were drowning in a mess of particles with no pattern and no order. Gell-Mann saw something the others missed. He noticed that the particles grouped into families, organized clusters with patterns in their charges and behaviors. If you accepted a simple idea, the whole zoo collapsed into something elegant. Everything could be explained if protons and neutrons were built from smaller pieces. 3 pieces each, tiny fundamental particles that combined in specific ways to produce every particle in the zoo. He named them quarks. He took the word from a line in a novel called Finnegan's Wake by James Joyce. The line reads, 3 quarks for muster mark. Nobody is completely sure why Gell-Mann chose it. The word meant nothing in physics. It just felt right. Across the country, a physicist named George Zweig reached the same conclusion independently. Same math, same structure. Different name. He called them aces. His paper landed on the desks of journal editors who rejected it. One reviewer reportedly called it the work of a graduate student trying too hard. Zweig never got the same recognition as Gell-Mann. That still sits uneasily in the physics community today, but neither man could prove quarks were real. The math worked beautifully. The patterns fit. However, nobody had ever detected a quark directly. Nobody had seen one, measured one, or caught one in a detector. And in physics, a beautiful idea without evidence is just a story. Most of the physics world treated quarks as a mathematical tool, a convenient fiction, a trick for organizing the data without actually describing reality. Serious physicists would use the quark model to calculate things, and then quietly agree that quarks probably did not literally exist. Gell-Mann himself hedged. In his original paper, he wrote that quarks might be real particles, or might just be useful mathematical objects. He was not sure. The theory described the world too well to ignore, but seemed too strange to fully believe. The strange part was the fractional charge. Every particle ever detected carried a whole number charge. Finding a particle with 2/3 of a charge would have been obvious. Detectors would have flagged it instantly. And nobody was finding anything like that. So where were they hiding? The answer would take 3 years and a machine the length of 2 miles to find. A team at a laboratory in California would fire electrons into protons at speeds close to the speed of light and watch what bounced back. What bounced back would change everything. The physics community had assumed protons were smooth, uniform spheres, solid all the way through. When electrons hit them, they expected the electrons to pass through or deflect gently, like a ball rolling through soft mud. Some of those electrons bounced back hard, almost straight back, like they had hit something small and dense buried inside the proton, something that was very definitely there. Gell-Mann was right, and the physics world had to catch up fast. But the confirmation created a new problem immediately. If quarks were real, and they were inside every proton and neutron ever detected, why had nobody ever seen one on its own? The answer to that question turns out to be one of the most violent and strange phenomena in all of physics. The year is 1964. The quark paper lands in front of some of the most respected physicists alive. Their reaction is not excitement. It is skepticism, bordering on dismissal. The fractional charge problem was the main target. Physics had spent decades building a clean picture of electric charge. Electrons carried exactly -1. Protons carried exactly +1. Every single particle ever measured matched this pattern. The numbers were whole. The rule felt unbreakable. Gell-Mann was proposing particles with charges of 2/3 and 1/3, numbers that had no place in that picture. And worse, particles that had never appeared in any detector anywhere, despite the fact that accelerators had been smashing atoms apart for years and cataloguing everything that came out. If quarks existed and carried fractional charges, they should have shown up by now. Detectors were sensitive enough to spot them. The absence of any signal was loud. Robert Serber, a prominent physicist at Columbia University, reviewed the paper and concluded quarks were a mathematical fiction, useful for organizing data, but almost certainly not real objects. He was not alone. The consensus among senior physicists leaned heavily toward the mathematical tool interpretation. Even the journals pushed back. George Zweig, who developed the same model independently, submitted his version to a major physics journal and got rejected. One of the reviewers called it the work of someone not ready for serious publishing. Zweig later said the experience was professionally damaging. The physics community had made up its mind before the evidence arrived. Part of the resistance was philosophical. Physics had a tradition of finding the simplest, cleanest building blocks: electrons, protons, neutrons. 3 particles to build the universe. Clean. Satisfying. The quark model required accepting that protons and neutrons were composite objects, built from smaller pieces with bizarre charge values. It added complexity at a level where physicists expected simplicity. There was also the isolation problem. Every particle discovered up to that point could, in principle, be pulled out and studied alone. Quarks could not. Gell-Mann's model implied they always appeared in groups, never alone. That had no precedent. A particle that physically could not exist in isolation felt less like a real particle and more like a mathematical ghost. And the name did not help. Taking the word from a James Joyce poem struck some physicists as frivolous. Science had a tradition of serious naming. Quark sounded like a joke, but the data kept coming in. The particle zoo that accelerators were producing kept matching the quark model's predictions with uncomfortable accuracy. Every time a new particle appeared, it slotted into the pattern Gell-Mann had drawn. The model worked too well to stay in the fiction category forever. The turning point came from an unexpected direction. A team in California was planning a series of experiments using a 2-mile-long accelerator. They were going to fire electrons into protons at enormous energy. Their goal was to map the inside of the proton in detail. Nobody expected what the data would show. The skeptics had built their case on the clean, smooth proton. If the proton was a uniform ball of charge with nothing interesting inside, the electrons would deflect at small angles and scatter evenly. Predictable, boring, confirming the existing picture. Some of the electrons did not scatter evenly at all. They bounced back at angles that made no sense for a smooth sphere. They were hitting something hard and small inside the proton, something with definite structure. The laughing stopped, but even after the evidence arrived, physicists faced a deeper problem. Accepting quarks as real meant explaining something that had no explanation yet. If quarks were real particles, why did the universe make it impossible to pull one out and examine it alone? What kind of force worked that way? The answer, when it came, was stranger than the question. The Stanford Linear Accelerator Center stretches 2 miles across the California flatlands. It is the longest accelerator ever built, and in the late 1960s, it became the place where quarks stopped being a theory and became a confirmed fact. The experiment had a straightforward goal: fire electrons into protons at high enough energy to probe what was inside. At lower energies, electrons bounce off protons in ways that suggest a smooth, uniform charge distribution. The idea was to push the energy high enough to see finer detail, the way a brighter light lets you see texture that a dim one misses. The team did not expect to find anything dramatic. Most physicists assumed the proton was essentially featureless inside, a smeared-out blob of charge with no hard structure. The electrons told a different story. At low angles, everything looked smooth, expected, but as the team analyzed electrons that came back at sharp angles, almost straight back the way they came, The numbers broke the smooth proton picture completely. Electrons scattered at those angles far more often than any uniform sphere would produce. One of the physicists on the team, Richard Feynman, visited Stanford during the experiments. He looked at the data and immediately saw what it meant. The electrons were bouncing off point-like objects inside the proton. Small, hard, dense things. He called them partons, meaning parts. He did not yet confirm they were Gell-Mann's quarks, but the structure was undeniable. The proton was full of smaller things. Over the next several years, the team gathered more data at different energies and angles. Each round tightened the picture. The hard objects inside the proton carried fractional electric charges, 2/3 and 1/3, exactly what Gell-Mann's quark model predicted. By 1973, the case was closed. Quarks were real. They lived inside protons and neutrons and nowhere else. The physics community that had laughed 6 years earlier now had to accept that the universe had a level of structure nobody had seen coming. The experiment earned 3 physicists the Nobel Prize in Physics in 1990. Jerome Friedman, Henry Kendall, and Richard Taylor received the award for the discovery. Gell-Mann had already received his Nobel in 1969, partly for the quark model itself, but the confirmation raised an immediate and unsettling question. If quarks are real particles inside the proton, and the electrons bounced off them clearly, why had nobody ever caught a quark flying out on its own? Smash enough protons together at high enough energy and you expect debris, fragments, pieces flying off in all directions. The Stanford experiments sent enormous amounts of energy into protons, and watched the results. Quarks never appeared alone in the debris. Something was keeping them locked inside, something that got stronger as the distance increased, rather than weaker the way gravity and magnetism both do. Every other force in nature fades with distance. This one grew. That was deeply strange. And it pointed toward a force nobody had fully described yet, a force so extreme that pulling 2 quarks apart does not free them. It creates something entirely new instead. The universe had put a lock on its own building blocks, and the key did not exist. What the team at Stanford had confirmed was only the beginning. Because the charges those quarks carried, 2/3 and 1/3, broke rules that had stood since the discovery of the electron. And the reason those broken rules work perfectly turns out to be one of the cleanest and most surprising puzzles in all of particle physics. For most of the 20th century, electric charge came in clean units. Electrons carried exactly -1, protons carried exactly +1. Every particle in every experiment matched this pattern. The unit of charge felt as fundamental as anything in physics. You could not have half of it. The universe did not work that way. Then quarks arrived, and the rule collapsed. Up quarks carry a charge of +2/3. Down quarks carry a charge of -1/3. These numbers had never appeared in physics before. They were not just unusual, they were supposed to be physically impossible based on every measurement ever taken. And yet they produce perfect results. A proton contains 2 up quarks. Add their charges together, 2/3 plus 2/3 plus -1/3. The answer is exactly +1, a clean, whole, familiar proton charge. The fractional pieces combine into something every detector had always measured correctly. A neutron contains 1 up quark and 2 down quarks, 2/3 plus -1/3 plus -1/3. The answer is exactly 0. A neutral particle, exactly as measured. The fractions were not a flaw in the model, they were the mechanism. The universe had been hiding fractional charges inside composite particles all along, and every measurement of a whole number charge was actually measuring the sum of smaller broken pieces underneath. This created a new question immediately. Why 2/3 and 1/3? Why those specific fractions and not others? No current theory gives a clean answer. The values work. The math confirms them. The reason the universe chose those numbers specifically sits in the category of genuine unknowns. and physicists will tell you honestly that they do not have a satisfying explanation. What made the confirmation especially strange was the detection problem. A particle with 2/3 of a charge would look completely different in a detector than anything ever seen before. It would leave a trail unlike any electron or proton. Decades of experiments had found nothing like that. The reason is confinement. Quarks cannot leave the proton. The force holding them inside gets stronger as they move apart, which means no matter how hard something hits the proton, the quarks stay grouped. They bounce around inside, but never escape as individual particles, so their fractional charges never appear alone in any detector. Only the combined whole number charge of the proton shows up on the outside. The fractional charges are real, measured, confirmed through multiple independent methods including the Stanford experiments and decades of follow-up work. But they exist in a kind of permanent quarantine inside every proton and neutron in the universe. Every atom in your body is held together by particles carrying charges that physics once declared impossible. And those particles are so locked inside their containers that the combined charge they produce is the only thing the outside world ever sees. The confinement that keeps their strange charges hidden is itself one of the most violent and extreme phenomena in nature. Understanding it required discovering an entirely new kind of force that behaves in ways that still seem backward even after decades of confirmation. But before that, there is another layer to the quark picture that makes the fractional charge story look almost simple. The universe does not just have one or two kinds of quarks, it has 6, and the reason for that number is one of the deepest unsolved questions in physics. 2 quarks build the visible universe, up and down. Everything you can touch, everything on Earth, every star you can see, runs on those 2. So why does nature need 4 more? Physicists call the different types of quarks flavors. The word has nothing to do with taste. It is just a label, the same way color charge has nothing to do with visible color. The 6 flavors are up, down, strange, charm, bottom, and top. They divide into 3 pairs, and each pair is heavier and more unstable than the one before it. Up and down quarks form normal matter, stable, long-lasting, the building blocks of protons and neutrons. The next pair, strange and charm quarks, only appear when something violent happens. A cosmic ray slamming into the upper atmosphere, a particle accelerator pushing collisions past normal energy limits. Strange quarks were actually the first hints that more than 2 quark types existed, appearing in unexpected particle decay patterns in the 1950s, before anyone had the quark model to explain them. The third pair, bottom and top quarks, require even more extreme conditions. The bottom quark was discovered at Fermilab in Illinois in 1977. The top quark took until 1995 at the same lab. It is the heaviest elementary particle ever confirmed. A single top quark weighs roughly as much as an entire gold atom. 1 particle. 1 atom's worth of mass. That comparison alone should stop you. All 4 of the heavier quarks are unstable. They decay into lighter quarks almost immediately after forming. Strange quarks decay in billionths of a second. Top quarks survive for less than 1/millionth of 1/billionth of a second before transforming into something else. They barely flicker into existence before vanishing. So why are they there? The honest answer is that nobody knows. The standard model of particle physics, the most successful scientific theory ever built, describes the 6 flavors accurately. It predicts their masses and behaviors. It does not explain why 6. There is no equation that requires exactly this number. There is no deeper law that demands nature stop at 6 and not continue to 7 or 8 or 20. Some physicists suspect the 3 pairs reflect a deeper symmetry in the universe that the current model does not fully capture. Others think 6 might be arbitrary, a result of how the early universe cooled, producing exactly this collection by chance. That second option is uncomfortable because it means the specific structure of all visible matter could have turned out differently. If the number of quark flavors is not fixed by some underlying rule, Then the periodic table of elements, the chemistry of life, the particular way stars burn, all of it rests on a foundation that might be more accidental than fundamental. That is a strange thing to sit with. And the 6 flavors are only one layer of the quark complexity. Each quark also carries something completely separate from its flavor, something physicists call color charge. And understanding color charge is where quarks start to seem less like particles and more like something the universe invented to break human intuition on purpose. Strip away the exotic. Forget the heavy, unstable flavors for a moment. 2 quarks build every piece of visible matter that has ever existed, up and down. And the way they combine to make protons and neutrons is so precise, so locked, that changing a single quark inside any nucleus would unravel chemistry itself. An up quark carries a charge of positive 2/3. A down quark carries a charge of negative 1/3. A proton contains 2 up quarks and 1 down quark. A neutron contains 1 up quark and 2 down quarks. Those are the only configurations that stable matter uses. Everything else decays. The proton has survived since minutes after the Big Bang. Scientists have tested proton stability by watching enormous tanks of water deep underground, waiting for a proton to spontaneously decay. In some experiments, the tanks sit for years. The proton outlasts the experiment every time. Current measurements suggest a proton may be stable for longer than 1,000 million years. The universe is only about 13 billion years old. That stability is not an accident. It comes from the specific way up and down quarks lock together under the strong nuclear force. Now consider what a single quark swap would do. If you changed 1 down quark in a neutron's nucleus to an up quark, the neutron becomes a proton. That happens constantly through radioactive decay. A neutron in an unstable nucleus can flip a down quark to an up quark through the weak nuclear force, releasing energy and changing the atom's identity entirely. Carbon becomes nitrogen, hydrogen becomes helium. Stars burn on exactly this process. The entire fusion engine of the Sun reduces to quarks swapping flavors at extreme temperatures and pressures. Every second, the Sun converts an amount of hydrogen equal to hundreds of millions of tons into helium. Each conversion involves down quarks flipping to up quarks inside neutrons, releasing the energy that crosses 93 million miles of space to warm your face. That is the reach of a single quark-type change. Up and down quarks are also almost identical in mass. The down quark is slightly heavier. That tiny mass difference matters enormously. If the up quark were heavier than the down quark instead, chemistry would be impossible. Protons would be unstable. They would decay into neutrons. Atoms as we know them would never form. The particular mass values of 2 quarks set the conditions for every element in the periodic table and every molecule those elements can build. Physicists have no explanation for why the up and down quark masses landed where they did. The Standard Model takes those values as inputs. It does not derive them from anything deeper. 2 numbers sit at the foundation of all chemistry, and no current theory explains why they are what they are. Everything from water to DNA to the electrical signals in your brain runs on the precise mass values of 2 quarks that physicists cannot yet explain from first principles. The heavier flavors, the ones that only appear in violent conditions, add a completely different layer. And the first hint that they existed came long before anyone had the tools to look for them properly. The universe runs on up and down quarks. Everything else is built for extremes. Strange quarks showed up uninvited. In the 1940s and 50s, physicists studying cosmic rays spotted particles that behaved wrong. They formed quickly in high-energy collisions, which suggested the strong nuclear force was involved. Then they decayed slowly, which suggested the weak nuclear force was doing the cleanup. The same particle could not logically involve both forces in such different ways. Scientists called these particles strange. The name became official. When the quark model arrived in 1964, The strange quark explained the oddity immediately. Strange quarks form fast because the strong force creates them. They decay slowly because only the weak force can transform them into lighter, up and down quarks. The strange quark was the universe's way of producing matter that does not quite belong in the stable world. Every strange quark eventually decays. It transforms into an up or down quark through the weak nuclear force, releasing energy as it falls to the lower level. The process takes billionths of a second. In particle physics terms, that is actually a long time. The short life still ends the same way every time, dropping back down to the stable pair. The charm quark arrived as a prediction before it arrived as a discovery. In 1970, two physicists independently calculated that a fourth quark flavor had to exist to make the theory consistent. The math broke without it. Certain decay rates came out wrong. Specific reactions showed up in calculations that never appeared in experiments. The only fix was a fourth quark with specific properties. In 1974, two different labs found it simultaneously. The particle appeared in both detectors on the same day. The physics community called the moment the November Revolution. The charm quark confirmed that the quark model extended beyond three flavors and that the math had been pointing at something real. Bottom and top quarks came next, completing the three pairs. The bottom quark discovery in 1977 was expected by then. The top quark took another 18 years. It required a machine powerful enough to generate the collision energy needed to produce something with the mass of a gold atom from scratch. The top quark survives for less time than light takes to cross a single proton. It forms, exists, and decays before it can even bind to another quark. Scientists measure its properties entirely through the debris it leaves behind. The particle itself is gone before any detector registers it directly. And yet the top quark matters. Its mass is so extreme that it interacts with the Higgs field more strongly than any other known particle. Some physicists believe the top quark plays a role in the stability of the universe itself. The exact mass of the top quark determines whether the universe is in a stable state or a metastable one, sitting in a temporary low point that could, in theory, flip to something different given enough time or the right nudge. One quark, one mass value, and the long-term fate of the universe hangs on where it lands. The heavier quarks live and die in tiny fractions of a second and leave the stable up-down world behind. Every time, but the force that holds all quarks together, regardless of flavor, is something even stranger than the quarks themselves, and it works through particles that have no mass at all. A proton weighs almost nothing, and yet its three quarks weigh even less. Add up the actual masses of the three quarks inside a proton, up quark plus down quark. The total comes out to roughly 2% of the proton's mass. The quarks themselves account for almost none of the particle they live in. The other 98% comes from gluons, particles with absolutely zero mass. That sounds like it should be impossible. How does a particle with no mass produce weight? The answer comes from Einstein's most famous equation. Energy and mass are interchangeable. The constant churning of gluons inside the proton, the energy of their motion and their interactions, converts directly into what a scale reads as mass. The proton weighs what it weighs almost entirely because of the kinetic energy of massless particles moving at the speed of light inside it. Extend that to your own body. If you weigh 150 pounds, roughly 147 of those pounds come from gluon energy. Your quarks account for about 3 pounds. You are mostly the energy of massless particles you will never see, moving at light speed inside structures smaller than anything a microscope can show. Gluons carry the strong nuclear force. They are the force itself made into a particle, the way photons carry the electromagnetic force. A quark emits a gluon, another quark absorbs it, and that exchange pulls the two together. The process happens constantly and at extraordinary speed inside every proton and neutron in the universe. But gluons have a property that makes them completely unlike photons. Gluons interact with each other. Photons, the carriers of light and electromagnetism, pass through each other without interaction. Gluons do not. They carry color charge themselves, and because they carry color charge, they attract each other the same way they attract quarks. This self-interaction is the reason the strong force behaves so differently from electromagnetism. It is the reason the force grows stronger at longer distances. When quarks get close together, the gluon field between them is relatively calm. When they pull apart, the gluons start bundling into a tighter and tighter tube of force. The field does not spread out and weaken the way a gravitational or electric field would. It constricts, it holds, it pulls back harder. Physicists call this a flux tube. As two quarks separate, the flux tube stretches between them. The energy packed into that tube grows with every fraction of a billionth of an inch they move apart. At some point, the energy in the tube becomes high enough to create two brand new quarks from nothing, one at each end. The tube snaps. Two quarks become four. The originals are still confined. The universe has solved the problem of isolation by making isolation physically impossible. This is not a theory. Scientists have directly simulated flux tube formation using lattice calculations, and the behavior matches experimental data precisely. Every attempt to isolate a quark produces new quarks instead of a free one. The force responsible for all of this runs on color charge, and color charge is where the physics leaves everything familiar behind entirely. Quarks have three properties that matter: flavor, electric charge, and color charge. The name color charge is completely misleading, and physicists know it. Quarks do not produce visible light. They are far too small to interact with photons in the way that creates color. The word was chosen because the math of color charge involves three values that combine to produce a neutral result. And the closest everyday example physicists could find was mixing red, green, and blue light to make white. The three color charges are labeled red, green, and blue. Every quark carries one of the three at any given moment. The rules of the strong nuclear force require that any stable group of quarks must be color neutral, colorless. A proton contains one red, one green, and one blue quark. Together, they cancel out. On the outside, the proton has no color charge at all. The quarks do not stay fixed to one color. They swap colors constantly by exchanging gluons. A red quark emits a gluon carrying red and anti-green charge, and when a green quark absorbs it, the first quark becomes green and the second becomes red. The colors shuffle continuously at speeds no human measurement can directly track. The stable requirement is not that each quark holds a fixed color, it is that the group always adds up to neutral. Antiquarks carry anti-colors: anti-red, anti-green, anti-blue. A quark and an antiquark can form a stable pair called a meson because one color and its anticolor cancel to neutral. These pairs are less stable than the three-quark proton. They decay quickly. But they follow the same color neutrality rule. Why three colors? This is genuinely not fully understood. The math of quantum chromodynamics works with three color charges and produces predictions that match every experiment ever run. If you try to build the theory with two colors or four colors, it breaks in specific ways that do not match reality. 3 is the number that makes the universe work. The reason the universe chose 3 has no satisfying explanation in any current theory. The color charge system produces one of the most striking predictions in physics. Single quarks cannot be color neutral. A red quark alone is unbalanced. The strong force will not allow an unbalanced color charge to persist. The universe responds by pulling the quark back toward a partner or by creating a new partner from energy before the quark can travel any meaningful distance. Color confinement, the rule that makes free quarks impossible. You can now run the full chain. Quarks carry color charge. Color charge must always be neutral in any stable particle. A single quark cannot be neutral, therefore a single quark cannot be stable, Therefore, no quark has ever been or ever will be detected alone, as long as the physics of this universe holds. This seems like a complete explanation, and for a long time, physicists treated it as one. Then someone asked what actually happens at the moment you try to pull two quarks apart. The answer did not just confirm confinement, it revealed something that looks for a moment like the universe is creating matter from pure violence. No quark has ever been found alone. In the entire history of particle physics, across every accelerator ever built, across millions of high-energy collisions producing debris that scientists sorted piece by piece, not a single quark has ever appeared as an isolated particle in a detector. This is color confinement, and it is absolute. Every other force in nature weakens with distance. Gravity follows an inverse square law. Double the distance, drop to 1/4 the strength. Electromagnetism does the same. Even the weak nuclear force, which governs radioactive decay, operates only at tiny ranges before becoming negligible. Every force you learned about in school gets weaker as things move apart. The strong nuclear force does the opposite. At extremely close distances, inside the proton, quarks barely feel it. They move almost freely, as if the force is barely there. This is confirmed by experiment and called asymptotic freedom, a property we will return to, but as quarks move apart, the force does not weaken. It holds steady. Then it grows. Think of it like a rubber band rather than a magnet. Magnets pull strongly when close, and weakly when far. A rubber band pulls weakly when barely stretched, and powerfully when stretched far. Quarks experience something closer to the rubber band. The further apart they move, the harder the force pulls them back. But the rubber band comparison breaks down at a critical point. A rubber band snaps when stretched too far and releases the tension. The strong force does something stranger. When enough energy packs into the field between two separating quarks, the universe does not release the quarks. It uses that energy to create two new quarks, one at each end of the stretched field. The original quarks are still confined. The new quarks are confined from the moment they appear. The attempt to isolate one quark has produced two additional quarks. This has been confirmed in accelerator experiments. When a particle collision blasts a quark away from its partners, the detector does not see a single quark flying out. It sees a jet of particles, dozens of new particles appearing along the path where the quark tried to escape. The energy of confinement converted into mass and produced a shower of new confined quarks and their composite particles. The confinement is self-healing. The universe patches the break immediately. Scientists have never found an exception. Every theoretical loophole has been explored and closed. Confinement holds at every energy scale ever tested. The mathematical framework that describes the strong force, quantum chromodynamics, predicts confinement perfectly, but cannot yet prove it from pure mathematics in a complete, rigorous way. This gap between physical prediction and mathematical proof is so significant that the Clay Mathematics Institute listed it as one of 7 unsolved Millennium Prize problems. Solving the confinement problem rigorously wins $1 million. The universe has been enforcing a rule that humans cannot yet fully prove from scratch. And the mechanism enforcing that rule, the actual moment-by-moment physical process of what happens when two quarks strain against each other, is where things move from strange to visually spectacular. The energy between them does not just grow, it takes a shape. Picture two quarks inside a proton. They are close together, moving at speeds approaching the speed of light, exchanging gluons constantly. At this distance, the force between them is almost relaxed. They move with relative freedom. Now imagine something hits that proton with enormous energy, a high-speed electron. Another proton traveling close to the speed of light. The collision transfers energy to one of the quarks and shoves it outward, away from its partners. The quark starts to move. The gluon field between it and the others does not spread out and weaken. Instead, the field compresses into a narrow tube. Physicists call this a flux tube, and lattice calculations have mapped its shape in detail. The field lines do not fan out like the field lines of a magnet. They stay bundled together in a cylinder of pure force, connecting the separating quark to its partners. As the quark moves outward, the flux tube stretches. The energy packed inside the tube grows with the distance, roughly proportional to how far the quark has traveled. The force pulling the quark back stays roughly constant, unlike any other force in nature. Picture it like pulling apart two ends of a thick elastic cord filled with compressed energy. The cord does not get thinner and weaker as you pull, it stays the same thickness. The energy inside keeps rising. The pull stays strong. At a certain point, something has to give. The energy inside the flux tube reaches the threshold where it equals the energy needed to create a new quark-antiquark pair from nothing. At that moment, the tube snaps. The energy converts directly into two new particles. A new quark appears near the separating end. A new antiquark appears near the original end. The two original quarks are still connected, now each to a new partner instead of each other. The quark that tried to escape is confined again immediately. It never traveled more than a tiny fraction of the width of a proton before the universe rebuilt the container around it. This process is called string breaking. It happens in every high-energy collision that tries to pull quarks apart. Scientists have confirmed the outcome in detectors, watching the jets of new particles that appear wherever a quark tries to escape. The shape of those jets, the angles and energies, match string-breaking predictions with precision. The universe enforces confinement with creation. Every attempt to free a quark results in more quarks. There is something worth sitting with here. The stuff inside every proton, inside every atom in your body, is held by a force so extreme that breaking it does not produce freedom. It produces more of the same thing. The universe responds to every attempt at isolation with multiplication. But what if you do not try to pull quarks apart? What if instead you pour so much energy into a system that the quarks no longer need to stay confined? What if you could recreate the conditions from the very beginning, before protons and neutrons existed at all? The answer to that question takes you back to the first microsecond of the universe. And what existed then is something physics has only recently learned to create on purpose. The flux tube is real. Scientists have not just theorized it, they have mapped it. Using a method called lattice quantum chromodynamics, researchers model the strong force on a grid of spacetime points and calculate the gluon field between two quarks as the distance between them increases. The results show a tube of color field lines bundled tightly together, stretching between the quarks. The tube has a roughly constant width of about 1 femtometer. For scale, a femtometer is 1 quadrillionth of a meter. A proton is about 1 femtometer across. The flux tube connecting two separating quarks is approximately the width of the proton they are trying to leave. As the quarks move apart, the tube stretches. The field inside it stays dense. The energy per unit length stays roughly constant. This is the origin of the linear potential that makes the strong force behave so differently from gravity or electromagnetism, where force fields spread out and thin as distance increases. The tension in a flux tube is enormous. Physicists estimate it at around 16 tons per square inch equivalent, concentrated into a region smaller than a proton. The universe is exerting forces that would tear apart any macroscopic material, but doing so at scales billions of times smaller than an atom. When the tube snaps, it does not disappear. The energy stored along its length converts into mass. A quark-antiquark pair materializes at the breakpoint. Each new particle carries the color charge needed to terminate the tube ends cleanly. The system returns to color neutrality in both halves immediately. This is pair production. It happens in other contexts in physics too. Extremely powerful electromagnetic fields can produce electron-positron pairs from vacuum energy. The strong force does the same thing, but under conditions that occur inside every high-energy proton collision anywhere in the universe. The quarks involved in the snap are not traveling from somewhere else. They do not exist before the tube breaks. The energy of the stretched tube converts to mass at the breakpoint, and the particles appear. Matter from pure energy. Confirmed by experiments, predicted by the math, still slightly unsettling to think about. Every time a particle accelerator smashes protons together at high speed, this process runs thousands of times per collision. Quarks try to escape. Tubes form and stretch. Tubes snap. Pairs appear. The detector fills with showers of new particles, each one already confined inside its own new proton or meson, before it registers on any sensor. Scientists read the angle and energy of those particle showers to reconstruct what happened inside the collision. The jets point back to the original quarks. The pattern of new particles encodes the properties of the flux tube that broke. The entire history of the collision is written in the debris, and in that debris, a consistent picture emerges. Quarks have never, in any collision, at any energy, escaped confinement. The energy to free them always becomes new quarks instead. The only known place in the universe where quarks have ever moved freely, unconfined, is the period immediately after the Big Bang, before protons existed, before the universe had cooled enough to let confinement take hold. That plasma of free quarks lasted less than 1/1,000,000th of a second. Scientists are now able to recreate it on purpose, and what they find inside it is reshaping the physics of the early universe. You have probably been told matter is made of atoms. Atoms are mostly empty space. The nucleus sits at the center, tiny and dense, surrounded by electrons far out in the surrounding emptiness. That is true, and also incomplete, because the nucleus itself is mostly energy. Inside every proton and neutron in your body, 3 quarks move at speeds close to the speed of light. They exchange gluons constantly. The gluons carry no mass. The quarks carry almost none. And yet all of that motion and interaction produces the mass you feel when you pick something up or step on a scale. Here is the number. If you weigh 150 pounds, your actual quarks weigh about 1.5 pounds. The rest of your weight, 148.5 pounds, comes from the kinetic energy of particles moving at extreme speeds and the binding energy of the gluon field holding them together. Energy behaves like mass at these scales. A scale cannot tell the difference. This is not an estimate. It follows directly from Einstein's equation relating energy and mass, applied to the measured quark masses and the known properties of the strong force. Now think about what this means for the concept of solidity. The desk you are sitting at feels hard because the electrons in your hand repel the electrons in the desk. The electromagnetic force between electron clouds creates the sensation of surface and resistance. The actual matter involved, the quarks, is a tiny fraction of the story. The hardness you feel is electromagnetic repulsion between nearly massless charge clouds surrounding nuclei that are themselves mostly gluon energy. Solid objects are force fields arranged in a shape. The quark content of your entire body could fit into a space much smaller than a single cell. The energy field around those quarks, maintained by massless gluons moving at the speed of light, creates everything else. Your height, your weight, the texture of your skin, all of it is held together by something that has no mass of its own. Different quark flavors contribute different amounts. Up and down quarks are the lightest. Strange quarks are heavier. The exotic flavors are heavier still. But all quarks are light compared to the protons they build. The top quark is the exception, heavier than a gold atom, but it decays too fast to build anything stable. For stable matter, the math is consistent everywhere. Most of the mass you measure is gluon energy converted into the appearance of solidity. Physicists have known this for decades. It has not changed how we think about everyday objects. Tables still feel solid. Floors still hold weight. But at the level where the physics actually operates, The universe built everything from almost nothing and made it feel permanent, using forces that have no mass of their own. That gap between physical experience and physical reality does not close. The bigger quarks, the unstable ones, had a different kind of weight problem. One of them weighs as much as a gold atom all on its own, despite being treated in the math as a point with no size. That contradiction sits at the edge of what the current theory can explain. In 1973, 3 physicists made a discovery so counterintuitive it almost did not get published. David Gross was working with his graduate student Frank Wilczek at Princeton. David Politzer was doing similar calculations at Harvard. They were trying to calculate how the strong nuclear force behaves at different distances and energy levels, particularly whether it gets stronger or weaker as quarks move closer together. Every other force they knew about got stronger as the particles got closer. Gravity pulls harder at short range. Electromagnetism intensifies between close charges. The assumption was that the strong force would follow the same pattern, maybe even more intensely, since the strong force was already the most powerful force in nature. The math gave the opposite answer. At extremely short distances, at very high energies, the strong force between quarks becomes weaker. Quarks very close together barely feel it. They move almost freely, and as the quarks move further apart, the force grows stronger rather than weaker. This broke the established pattern so completely that Gross initially thought he had made a mathematical error. He checked it. Wilczek checked it. Politzer's independent calculation confirmed the same result. The strong force was unlike every other force in nature. It had an inverse relationship with distance. Close together means weak. Far apart means strong. They named it asymptotic freedom. Asymptotic because the force approaches zero as the quarks approach each other at very high energies, meaning they are free in that limit. This discovery earned Gross, Wilczek, and Politzer the Nobel Prize in Physics in 2004. Asymptotic freedom explained something that had puzzled physicists since the Stanford experiments. When electrons were fired into protons at very high energies, the quarks inside behaved as if they were nearly free, almost unbound. The electrons were probing the proton at extremely short distances, and at those distances the strong force was almost silent. The quarks moved freely inside the proton at high energy because at short range they barely interacted. Pull them apart, and the force wakes up. This backward behavior comes from the self-interacting nature of gluons. Gluons carry color charge and attract each other. As quarks move apart, the gluon field bundles into the flux tube, concentrating force rather than spreading it. As quarks move together, the gluon field has less room to concentrate, and the force drops. The geometry of the gluon field drives the behavior of the force in opposite directions, depending on distance. Asymptotic freedom has a consequence that connects directly to the early universe. If the strong force weakens at high energies and short distances, then at extremely high temperatures, where all particles are packed incredibly close and moving at enormous speeds, quarks should be free, unconfined, moving through a sea of other quarks and gluons without binding into protons or neutrons. This is exactly what happened in the first moments after the Big Bang, and it is exactly what physicists can now create in particle accelerators for the briefest possible moments. But the implications of asymptotic freedom go further. It solved a problem that had haunted the quark model for years and set up the complete mathematical framework for the strong force. That framework makes extraordinary predictions, and it holds up to every test ever designed, except one. A proof that the force actually confines quarks in rigorous mathematics remains unfinished. And that unfinished proof is worth $1 million to whoever completes it. A proton is unimaginably small. If you lined up 100 million protons side by side, you would barely cover the width of a human hair. And inside each one, 3 quarks are moving at speeds that approach the speed of light itself. That comparison needs context. The speed of light is about 670 million miles per hour. Nothing with mass can actually reach it. But quarks inside a proton travel at a substantial fraction of that speed, moving in a space smaller than 1/millionth of an inch across. They are some of the fastest moving things in the known universe, trapped in some of the smallest containers. The confinement is not passive. Quarks do not sit still inside the proton the way marbles sit in a jar. They move, they interact. They exchange gluons in a continuous process that happens at timescales far beyond any human measurement. The proton is dynamic at every instant. Its interior is a constant, violent storm of particles moving at nearly light speed and exchanging force carriers millions of times per second. This motion is part of why the proton has the mass it does. Kinetic energy at these speeds behaves as mass through Einstein's equation. The faster the quarks move, the more the proton weighs. Most of that weight is motion. The quarks are essentially running in place at near light speed inside a container they cannot leave, and the energy of that running registers on a scale as the proton's mass. There is something strange here about size. A quark is treated in the mathematics of quantum chromodynamics as a point particle. Zero size, no internal structure detected at any energy scale ever tested. The proton has a definite size, roughly 1 femtometer across, but the quarks inside it have no measurable size. They are dimensionless objects, moving at nearly the speed of light through a space that is itself extraordinarily small. Physicists use the term size with some caution when talking about quarks. What experiments measure is an upper limit on quark size, the smallest scale at which any substructure or deviation from point-like behavior has been detected. At every energy scale tested so far, quarks behave as perfect points. The true size may be 0, or maybe something smaller than any current accelerator can resolve. If quarks do have substructure, finding it would require energies far beyond anything built so far. The question of whether quarks are truly fundamental, or whether they are themselves made of something smaller, remains genuinely open. The proton is also not the simple static 3-quark system that textbooks often draw. Inside the proton, gluons constantly split into temporary quark-antiquark pairs that exist for a tiny fraction of a second before annihilating back into gluons. These are called C-quarks. At any given moment, the proton contains its 3 permanent quarks, called valence quarks, plus a constantly changing sea of temporary quark-antiquark pairs created and destroyed by the gluon field. The picture of a proton as 3 dots in a circle is useful for learning. The physical reality is closer to a violently churning sea of particles appearing and vanishing in a space smaller than anything visible. And one quark stands completely apart from this picture, a quark so heavy it cannot survive long enough to be confined inside a proton. A quark that forms and vanishes before the strong force can even begin to bind it, and its mass sits at a value that touches something much bigger than particle physics. In 1995, a team at Fermilab in Illinois confirmed the existence of the top quark after an 18-year search. It had been predicted. The math required it. But producing one required collision energies that pushed the limits of the largest accelerator operating at the time. The top quark is the heaviest elementary particle ever confirmed. A single top quark weighs about as much as an atom of gold. Gold, element 79, is one of the densest and heaviest atoms that occurs naturally on Earth. Its atom contains 79 protons, 118 neutrons, and 79 electrons. Every single component of that gold atom, hundreds of particles, and yet a single top quark matches its total mass. Gold atoms are composed of quarks. So is the top quark, according to the Standard Model. Definitively not. The top quark is a fundamental particle. It has no internal structure detected at any resolution. It is treated mathematically as a point, 0 size, and it outweighs the entire gold atom it could theoretically be compared against. This creates a tension in the theory. The Standard Model has no equation that predicts what the mass of any quark should be. It takes quark masses as inputs from experiment. A physicist cannot sit down and calculate that the top quark must weigh a gold atom. They measure it, and write the number in. The model then uses that number to make other predictions. Why is the top quark so heavy? No one knows. The other quarks, up through bottom, span a range from the lightest at tiny fractions of a proton mass to the bottom quark at a few proton masses. The top quark sits at roughly 180 times the mass of a proton. It is not just the heaviest quark, it is the heaviest elementary particle by a factor that has no theoretical explanation. The top quark's extreme mass makes it interact with the Higgs field more strongly than any other known particle. The Higgs field is the field that gives other particles their mass. The stronger a particle interacts with it, the heavier the particle is. The top quark couples to the Higgs field at a strength close to 1, which in the language of particle physics means the interaction is nearly as strong as it could possibly be. This appears to be a clue about something deeper, but what exactly it points toward is still an open debate. The top quark also plays a role in the long-term stability calculations of the universe. The precise value of the top quark mass, combined with the mass of the Higgs boson, determines whether the vacuum state of the universe is in a true minimum energy state or a temporary one. Current measurements place the universe in a region called metastable, meaning the vacuum could in principle tunnel to a lower energy state given an unlikely quantum fluctuation. The universe has existed stably for about 13 billion years, so this is a slow process if it happens at all. But the top quark mass sits at the boundary of these calculations, and small shifts in its measured value push the conclusion towards stable or metastable. One particle's mass, one number, measured in a laboratory in Illinois. And it touches the question of whether the universe, as it exists now, could, over incomprehensible timescales, spontaneously reorganize into something different. The top quark decays before the strong force can bind it into a hadron. It exists for less time than light takes to cross a proton, and in that microscopic instant, it leaves fingerprints on questions about the fate of the entire universe. The early universe was filled with top quarks, and every other quark flavor moving freely. That free state, the quark-gluon plasma, existed before protons existed, and scientists have now learned to recreate it. 1 microsecond after the Big Bang, the universe had no protons, no neutrons, no structure of any kind. The entire universe was a single, unimaginably hot soup of quarks and gluons moving freely through each other, unconfined, unbound. Physicists call this state the quark-gluon plasma, and it is the most extreme form of matter that has ever existed. The temperature at that moment was roughly 2 trillion degrees. For comparison, the center of the Sun sits at about 27 million degrees. The quark-gluon plasma was roughly 100,000 times hotter than the core of a star. At that temperature, the energy per particle was so high that the strong force could not bind quarks into protons. Asymptotic freedom ruled. Quarks moved freely because at those energies and distances, the strong force essentially switched off. Then the universe expanded. It cooled, and as the temperature dropped below that critical threshold, something happened that took less than a microsecond and defined every structure that has ever existed since. The quarks suddenly became confined. Protons and neutrons snapped into existence across the entire universe simultaneously, wherever the conditions allowed. The quark-gluon plasma froze into hadronic matter, meaning matter made of particles like protons and neutrons. This transition is called the QCD phase transition, and it is one of the most significant events in the history of the universe. Before this transition, quarks were free. After it, they have been locked inside protons and neutrons for 13 billion years and counting. The plasma that existed before has been gone for almost the entire history of the universe. Studying it directly seems impossible, and yet scientists have found a way. Heavy ion collisions at the Large Hadron Collider at CERN and at the Relativistic Heavy Ion Collider in New York slam gold or lead nuclei together at energies close to the speed of light. For a brief window measured in tiny fractions of a second, The collision recreates temperatures comparable to the early universe. The quarks inside the colliding nuclei temporarily lose their confinement. They flow freely through each other in a droplet of quark-gluon plasma lasting about 10 to the power of -23 seconds. That droplet is smaller than a proton and gone almost instantly, but the particles that fly out carry information about the plasma's properties. Scientists study those particles carefully. What they found surprised almost everyone. The quark-gluon plasma does not behave like a gas of freely moving particles, which was the original expectation. It behaves like a liquid. Specifically, it flows like an almost perfect fluid with near-zero viscosity. It moves more smoothly than any fluid ever measured in a laboratory. Liquid helium near absolute zero, the most frictionless substance humans had previously created, has significantly more internal resistance than quark-gluon plasma. The earliest matter in the universe flows more perfectly than anything we have created in 13 billion years of cosmic history. This tells physicists something unexpected. Even in the free phase, quarks and gluons interact strongly with each other. The plasma is not an ideal gas of independent particles. The interactions between quarks and gluons in the plasma create collective behavior, a fluid that moves as one. The universe that existed before protons formed was a perfect, almost frictionless sea of quarks. And what happened when that sea froze into protons and neutrons, specifically why it produced more matter than antimatter, remains one of the deepest unsolved problems in all of physics. Building a machine that can recreate the first microsecond of the universe requires more than engineering. It requires understanding what you are looking for before you find it. The Large Hadron Collider at CERN sits in a circular tunnel 27 kilometers around, buried 100 meters underground, on the border between France and Switzerland. It accelerates particles to within a fraction of a percent of the speed of light and smashes them together. At full power, the collision energy reaches levels that existed in the universe fractions of a second after the Big Bang. For quark-gluon plasma experiments, the collider does not use protons. It uses lead ions, the nuclei of lead atoms, stripped of all their electrons. Each lead nucleus contains 208 protons and neutrons packed tightly together. When two lead nuclei collide at near light speed, the collision does not just break protons apart, it superheats the entire nuclear material, driving the temperature high enough to melt confinement itself. The collision lasts an almost incomprehensibly short time. The plasma droplet that forms is smaller than a proton. It cools and freezes back into normal hadrons in less than a blink of time. Then the particles fly outward into the detector. Reading the debris of a quark-gluon plasma collision is like trying to reconstruct a car crash from the scattered pieces. Scientists measure the angle, energy, and type of every particle that reaches the detector. From those measurements, they work backward to reconstruct what happened during the collision. One key signal is called jet quenching. In normal proton collisions, high-energy quarks produce jets of particles that fly outward in pairs, back to back. In a quark-gluon plasma collision, one jet often goes missing or arrives weaker than expected. The interpretation is that the jet traveled through the plasma and lost energy to the surrounding quark-gluon soup. The plasma absorbed the jet's energy the way a thick fluid absorbs an object pushing through it. Another signal comes from particles called J-psi mesons, which contain a charm quark and its antiquark. In normal matter, these form readily. In quark-gluon plasma, the plasma separates charm quarks from their partners before they can bind. Fewer J-psi mesons escape. The suppression of these particles in heavy ion collisions is a direct signature of the plasma state. The relativistic heavy ion collider in Brookhaven, New York, running gold-gold collisions, provided the first strong evidence that the quark-gluon plasma flows like a liquid rather than a gas. The elliptic flow patterns of particles emerging from off-center collisions matched the predictions for a nearly perfect fluid and matched nothing else. These experiments gave physicists a tool to test theories about the early universe that no telescope could provide. The universe from 1 microsecond after the Big Bang left no direct light signal. The cosmic microwave background, the oldest light we can detect, comes from 380,000 years after the Big Bang, long after quarks were already confined. The only way to probe the quark epoch is to recreate it. Scientists are doing that now, in controlled conditions, under a mountain in Switzerland. What the plasma experiments cannot yet fully answer is the deepest mystery the quark-gluon plasma raises. When the universe cooled and quarks froze into protons and neutrons, there should have been equal amounts of matter and antimatter. Equal quarks and antiquarks. They should have annihilated each other completely, leaving nothing behind. The universe you are living in should not exist. And yet here it is. At the moment of the Big Bang, the universe created quarks and antiquarks in pairs. For every quark born, an antiquark came with it, equal and opposite. The rules of physics as scientists understand them demand symmetry between matter and antimatter. Create one, create the other. Always balanced. If the universe followed those rules perfectly, every quark would have found an antiquark. They would have collided, annihilated each other. Converted back to pure energy, the universe would have ended as a sea of photons with no matter, no atoms, no stars, no anything. And yet, somewhere in the first fraction of a second, the balance broke. For every 1 billion antiquarks, there were 1,000,000,001 quarks. A tiny excess. One extra quark for every billion pairs. The antimatter and matter annihilated each other completely, as expected. The one extra quark per billion survived, and that tiny surplus of quarks, multiplied across the entire volume of the early universe, became every proton and neutron that exists today. Every galaxy, every star, every planet, every atom in your body, all of it descended from a 1 in a billion surplus of quarks over antiquarks in the first moments of the universe. Physicists call this imbalance baryogenesis. The conditions needed to produce it were first laid out by the Soviet physicist Andrei Sakharov in 1967. He identified 3 requirements. The laws of physics must treat matter and antimatter differently. This difference is called charge parity violation, and it has been measured in certain quark decay processes. The amount of charge parity violation found in quarks so far, though real and confirmed, is far too small to explain the observed excess of matter. The current measured imbalance in quark behavior can explain only a tiny fraction of the matter that exists. Something else produced the rest. Either there is an unknown source of charge parity violation that physics has not yet found, or there are processes in the early universe that existing theories do not describe. This is one of the biggest open questions in all of science. The reason matter exists at all, the reason you exist, cannot yet be fully explained. The quarks and their behavior give physicists a place to look, but the complete answer has not been found. What makes this stranger is that the antiquarks produced in the Big Bang were not just passive partners to the quarks. They were identical in almost every way, carrying the same mass, the same color charge, the same fractional electric charge but with opposite sign. An up antiquark carries negative 2/3. A down antiquark carries positive 1/3. And if one of these particles ever meets its matter twin, the result is immediate and total. The violence of that meeting is something that happens in particle accelerators every second. An antiquark is the mirror image of a quark in almost every measurable way. Same mass, same color charge behavior, same fractional electric charge, but flipped in sign. An up antiquark carries negative 2/3. A down antiquark carries positive 1/3. They obey the same confinement rules as regular quarks and live inside antiprotons and antineutrons the same way quarks live inside their matter counterparts. Antiprotons exist. They have been produced in accelerators and studied in detail. Scientists at CERN have created antihydrogen, a positron orbiting an antiproton, and trapped it long enough to measure its spectral lines. The spectral lines of antihydrogen match hydrogen with extraordinary precision. Matter and antimatter appear to behave identically under most conditions. Now picture what happens when a quark and its antiquark meet. The collision is total. Both particles vanish in an instant, converting entirely to energy, usually in the form of high-energy photons or other particle pairs. Mass converts to pure energy at 100% efficiency. Nuclear weapons achieve less than 1% conversion of mass to energy. A matter-antimatter collision loses nothing. Every bit of mass becomes energy. In accelerators, when a proton and antiproton collide at high speed, the individual quarks and antiquarks inside them find each other and annihilate. The resulting energy produces showers of new particles. This is one of the primary ways scientists create the heavy, unstable quark flavors. Enough energy from annihilation converts back into mass and produces particles that exist nowhere else in the natural universe around us. The Tevatron accelerator at Fermilab ran for decades on proton-antiproton collisions. The annihilation energy from those collisions produced top quarks, bottom quarks, and W and Z bosons. Each discovery traced back to the moment a quark inside the proton met its antiquark twin inside the antiproton, and both ceased to exist. There is a practical limit to studying antimatter. Creating it requires enormous energy. Storing it requires magnetic traps that keep it from touching any matter container. CERN's antihydrogen experiments trap atoms for minutes using magnetic fields. Creating a gram of antimatter using current accelerator technology would require more energy than the entire world produces in thousands of years. The question of why the universe chose matter over antimatter by that tiny margin sits unresolved. The charge parity violations measured in quark systems are real but insufficient. Physicists are expanding the search into other particle systems, particularly neutrinos, looking for additional sources of asymmetry that might close the gap. But even setting aside the matter-antimatter imbalance, quarks have another transformation mechanism that drives the entire nuclear activity of stars and determines the chemical identity of every atom. A quark can change its flavor entirely through a force that operates by completely different rules from the strong force. And that transformation is happening inside stars right now, including the one that makes life on Earth possible. The strong nuclear force holds quarks together. It does not change them. A different force handles transformation. The weak nuclear force can take a down quark and convert it into an up quark, or reverse the process. The quark keeps its color charge. It keeps its confinement inside the proton or neutron, but its flavor changes, and when a flavor changes inside a nucleus, the entire atom changes identity. This is radioactive beta decay. A neutron contains one up quark and two down quarks. The weak force converts one of those down quarks into an up quark. The neutron becomes a proton. The nucleus gains a proton. The element changes. Carbon becomes nitrogen. Phosphorus becomes sulfur. The periodic table is not fixed at the nuclear level. Atoms can transform through quark flavor changes. The weak force operates through particles called W and Z bosons. Unlike gluons, these force carriers are extremely heavy. The W boson weighs roughly 80 times as much as a proton. This mass is why the weak force has such a short range. Heavy force carriers cannot travel far. The weak force operates only within a distance much smaller than a proton. In the quark flavor change, a down quark emits a W boson and becomes an up quark. The W boson then decays, producing an electron and an antineutrino. These particles fly out of the nucleus, while the converted quark stays confined inside the new proton. The whole process happens in a time that varies depending on the nucleus, from fractions of a second for unstable isotopes to billions of years for stable ones. This flavor-changing ability connects quarks to the entire energy output of stars. The Sun fuses hydrogen into helium through a chain of reactions that depends on weak force quark transformations at each step. Without the weak force changing quark flavors, hydrogen fusion does not proceed. Stars do not ignite. There is no solar energy, no warmth reaching Earth, no conditions for life. The weak force also plays a role in the matter-antimatter imbalance. It treats quarks and antiquarks slightly differently. This was first measured in kaon decays in 1964, just months after the quark model appeared. Kaons are particles containing strange quarks, and their decay rates showed a small but definite asymmetry between matter and antimatter behavior. The asymmetry is real. The amount remains too small to explain the universe's matter surplus. Scientists continue measuring quark decays across multiple particle types, searching for any additional source of the imbalance. But beyond flavor change, quarks participate in a broader family of composite structures than most people realize. Protons and neutrons are the stable members of a much larger family of quark combinations, and some of those combinations should not be able to hold together at all, according to older versions of the theory. They do anyway. A proton has survived since a few minutes after the Big Bang. It has not sat still the entire time. The interior of a proton is one of the most active environments in nature. Quarks move at near light speed. Gluons appear and disappear. Temporary quark-antiquark pairs flicker into existence and vanish. The proton is in constant internal motion across timescales too small to measure, and yet from the outside, it is perfectly stable. This combination, violent internal activity and external permanence, reflects a deep principle of the strong force. The proton as a whole is color neutral. Its total electric charge is exactly +1. Its total energy sits at the minimum possible for a 3-quark system with those quantum numbers. There is nowhere lower for it to fall. No decay channel is available that conserves all the required properties. Stability does not mean stillness. It means the system has no energetically favorable way to change its external properties. Neutrons tell a different story. A free neutron, one sitting alone outside a nucleus, decays in roughly 15 minutes on average. The weak force converts one of its down quarks to an up quark, and the neutron becomes a proton. Inside a nucleus, this decay is suppressed. The nuclear environment changes the energy landscape. A neutron bound inside a stable nucleus has no available decay path because the resulting proton state is already occupied or energetically unfavorable. Stable nuclei keep their neutrons locked. The internal sea of the proton includes more than 3 quarks at any moment. The gluon field constantly generates temporary quark-antiquark pairs called C-quarks that appear and vanish in timescales too brief to observe directly. These C-quarks contribute to the proton's properties in measurable ways. High-energy electron scattering experiments reveal the C-quark contribution through momentum distributions inside the proton. The proton contains traces of strange charm and even bottom quarks at any given moment, living briefly as C-quarks before annihilating back into gluons. The proton's spin creates another puzzle. A proton has a definite quantum spin of 1/2. Physicists assumed this spin came primarily from the 3 valence quarks inside. Experiments in the 1980s and 90s showed that the quarks contribute only about 30% of the proton's spin. The rest comes from gluons and the orbital motion of all the quarks inside. The proton spin crisis, as it became known, revealed that the internal structure of even the most familiar particle is far more complex than the simple 3-dot picture suggests. Decades of experiments have refined the picture. The proton spin involves contributions from gluons, C-quarks, and orbital angular momentum in ways that active research programs at facilities worldwide are still working to map precisely. This stability of the proton, despite its turbulent interior, provides the foundation for all of atomic chemistry. But protons are only one arrangement of quarks. Other arrangements exist, some stable enough to detect, others flickering in and out of reality faster than any instrument can directly record. And a few of these arrangements broke a rule that physicists had considered settled for half a century. For most of the 20th century, the rule seemed simple. Quarks combine in two ways. 3 quarks make a baryon. A quark and an antiquark make a meson. Every particle ever detected fit one of these two categories, and the theory gave no strong reason to expect anything else. Then, accelerators pushed to higher energies, and particles started appearing that refused to fit. A hadron is any particle made of quarks. Protons and neutrons are the most stable baryons. Pions and kaons are common mesons. These fit the textbook picture. But the textbook picture was built from a simplified version of quantum chromodynamics that allowed only 2 and 3 quark combinations for practical reasons, not theoretical ones. The actual theory of the strong force places no firm limit on the number of quarks in a stable combination, provided the total color charge cancels to neutral. 4 quarks can combine if 2 are quarks and 2 are antiquarks. 5 quarks can combine if 4 are quarks, and 1 is an antiquark. The color math works out. The question was whether nature actually produced these states, or whether they were mathematical curiosities. Nature produces them. The first confirmed tetraquark, a 4-quark state, was observed at the Bell experiment in Japan in 2003. A particle called X, 3872, appeared in collision data with properties that could not be explained by any 2-quark or 3-quark combination. Its mass, decay patterns, and quantum numbers matched a 4-quark state. Since then, dozens of exotic hadron candidates have been identified. The Large Hadron Collider Beauty experiment has been particularly productive, confirming multiple tetraquark and pentaquark states in the past decade. In 2015, the same experiment confirmed the existence of pentaquarks, 5-quark states. For the first time, a particle containing 4 quarks and 1 antiquark showed up in the decay products of a bottom quark hadron. How does science find these particles? The process relies on reconstructing mass from collision debris. When a known particle decays, the products carry a combined mass equal to the parent. If scientists calculate the combined mass of a set of decay products and find a sharp peak at a specific value repeated across thousands of collisions, that peak is a particle. The mass and decay mode identify it. Exotic hadrons tend to appear near thresholds, energies just above the point where 2 ordinary hadrons could combine. Some physicists argue that many of the observed exotic states are actually loosely bound molecules of 2 ordinary hadrons, rather than tightly bound 4 or 5 quark states. The distinction matters for understanding the strong force. Whether the new states are true multi-quark particles or hadronic molecules changes the theoretical picture significantly. The experimental evidence for exotic hadrons is solid. What they are internally, how tightly their quarks bind, and whether further arrangements beyond 5 quarks exist remain open questions. The existence of these states tells physicists that the strong force allows a wider family of quark structures than any 20th century textbook described. And some of the most recently confirmed structures push into territory where the theory's predictions are least certain. X, 3872, should not have lasted long enough to detect. 4 quarks held together looked, in the older models, like a configuration that would immediately fall apart. 2 quarks and 2 antiquarks have plenty of ways to split into pairs and decay. The decay channels are wide open. Early theoretical work suggested fully bound tetraquarks would be so short-lived that finding a clear signal for them would be nearly impossible. But the signal appeared, sharp, repeated, unmistakable. The particle physicists now call X, 3872, contains a charm quark, an anti-charm quark, and an anti-up quark. Its mass sits just below the threshold where it would naturally decay into 2 charmed mesons. That position near the threshold may be the key to its relative stability. The decay is energetically barely possible, which slows it down compared to particles that decay with large energy release. The pentaquark states confirmed in 2015 at the Large Hadron Collider Beauty experiment came from a different direction. Scientists were studying the decay of a baryon containing a bottom quark. In the decay chain, unexpected intermediate states appeared with masses and quantum numbers that required 5 quarks to explain. 2 pentaquark states were confirmed, later refined to 3, each containing 4 quarks, and 1 antiquark. The internal structure of pentaquarks is still debated. One picture shows 5 quarks tightly bound in a single bag by the strong force, a genuinely new type of hadron. Another picture shows a charmed baryon and a charmed meson orbiting each other loosely, a hadronic molecule held together by residual strong force effects rather than direct quark binding. Distinguishing between these two pictures requires measuring the internal structure of the pentaquark directly, which current detectors cannot yet do. This is standard scientific territory. The existence of the particle is confirmed. Its internal architecture is still being mapped. What is clear is that the 2 or 3 quark picture of hadrons was always an approximation. The universe permits richer combinations. Glueballs, particles made entirely of gluons with no quarks at all, are predicted by quantum chromodynamics and have been searched for since the 1980s. Candidate glueball states have been found, but none confirmed beyond reasonable doubt. Hybrid hadrons, particles containing quarks plus an excited gluon contributing to the quantum numbers, are also predicted. Evidence for hybrid candidates exists. Confirmation awaits cleaner experimental signals. The zoo of possible hadronic states is larger than physicists thought. In 1964, when Gell-Mann named the quark, the basic architecture of the quark model held up. The specific limit of 2 and 3 only did not. Every new exotic state confirmed at an accelerator adds a data point to the question of how far the strong force's creative capacity extends. And below all of it sits the question that the quark model itself cannot answer. If quarks are the building blocks, what are quarks built from? The answer might be nothing. Or it might be something physics has not yet reached the energy to detect. Every time physics found a new layer, it was because someone built a machine powerful enough to look deeper. Atoms seemed fundamental until the electron appeared. The nucleus seemed solid until protons and neutrons split it apart. Protons seemed elementary until the Stanford experiments found quarks inside them. Each step required more energy to probe smaller scales. Quarks have now withstood every probe built so far. At every energy level tested, they behave as perfect points. No internal structure, no deviation from point-like behavior, no sign of anything smaller. But this is a limit of our tools, not a limit of the universe. Experiments measure what they have the energy to resolve. Smaller structures, if they exist, would require higher energies to reveal. The current upper limit on quark size, the smallest scale at which experiments would have seen substructure if it were there, is about 1,000th the size of a proton. Anything smaller than that remains invisible to existing accelerators. The question of whether quarks are truly fundamental or whether they have internal structure at scales we cannot yet reach is genuinely open. The standard model treats quarks as fundamental with no further layers. This is consistent with all current data. It is not proven to be true for scales below current experimental reach. History argues for caution. Atoms were fundamental. Protons were fundamental. The pattern of each layer revealing a deeper one has held for over a century. Nothing in principle prevents it from continuing. Quarks might be the final layer. They might be the latest in a series that continues to scales where new physics operates. What makes this particularly difficult is that the strong force itself obscures the interior. Even if quarks had substructure, the intense gluon field inside the proton would affect how any probe interacts with the interior of a quark. Separating internal quark structure from strong force effects would require theoretical clarity. that does not yet exist alongside experimental reach that does not yet exist. Some physicists take a philosophical position. They argue that the concept of a final, truly elementary particle may not be the right framework. Quantum field theory describes particles as excitations of underlying fields. At deep enough levels, the distinction between particle and field, between fundamental and composite, may stop being meaningful. The question, what is inside a quark, may eventually become a question that the physics of the future does not ask in that form. That is, speculation. For now, the practical reality is that quarks are the smallest things confirmed to exist inside matter, with no detected substructure, and the next step down is unknown territory. Some physicists have tried to map that unknown territory using theory alone. The most developed attempt has a name, preons, and a set of predictions. None of those predictions have been confirmed, but the theory remains alive, and the reasoning behind it addresses a question the Standard Model leaves open in a way that bothers physicists who like their answers clean. The Standard Model has a problem that nobody talks about enough. It contains too many inputs with no explanation. There are 6 quarks, 6 leptons, the family of particles that includes the electron, 4 fundamental forces. Each particle has a specific mass that the theory takes from experiment and inserts as a given. The model does not explain why the electron has the mass it has, why the top quark is so much heavier than the up quark, or why there are exactly 3 generations of matter particles. To some physicists, this looks like the periodic table did in the 19th century. Before atomic theory, the periodic table was a pattern without a reason. Similar elements appeared in columns, properties repeated with a structure that was clearly meaningful. The explanation came when scientists discovered that atoms were made of protons, neutrons, and the periodic table was just the map of how those pieces could be arranged. Preon theory proposes the same logic applied to quarks and leptons. If a simpler layer of particles exists below quarks and leptons, the pattern of 6 quarks and 6 leptons might emerge naturally from how those smaller pieces combine, the way the periodic table emerges from atomic substructure. The proposed subparticles are called preons. Different versions of preon theory propose different numbers of fundamental preons. Some models use 2, some use 3. Each model attempts to reproduce the known quarks and leptons as composite particles, made of preons bound by a new force that operates at scales smaller than anything yet measured. The experimental problem is severe. For quarks to be composite, their constituents must be bound by forces much stronger than the strong nuclear force itself. Operating at distances much smaller than a proton, the energy required to probe that scale exceeds the capacity of any accelerator ever built or currently planned. Preon theories also face a specific physics challenge called the compositeness problem. Quantum mechanics requires that if a particle is made of smaller parts, the uncertainty in the position of those parts produces enormous kinetic energy. For a particle the size of a quark to be composite, the binding energy holding its preons together must cancel this kinetic energy almost perfectly. The cancellation required is so precise that it seems contrived. Physicists call this problem unnatural. No preon model has produced a confirmed prediction. No experiment has detected any deviation from point-like quark behavior that would hint at internal structure. Preon theory remains alive because the motivation is real. The Standard Model's parameter problem is genuine. Some physicists believe the cleanest resolution is a deeper layer. Others believe the parameters are simply the way the universe happened to set up, and no deeper explanation exists. The debate connects to a broader tension in modern physics between the desire for explanatory depth and the acceptance of unexplained inputs. And nowhere is that tension sharper than in the mathematical framework that describes quarks themselves, a theory that works with extraordinary precision and yet breaks down in ways its own creators admit remain unresolved. Quantum chromodynamics is the theory of the strong nuclear force. It describes how quarks interact through gluons and color charge. It is one of the most precisely tested theories in the history of science. It is also incomplete. Physicists built quantum chromodynamics in the early 1970s using the same mathematical framework that describes electromagnetism at the quantum level, a framework called quantum field theory. The theory treats quarks and gluons as excitations of underlying fields and calculates interactions by summing over all possible ways an interaction can occur. For electromagnetism, this method works beautifully at all energy scales. The calculations can be organized as a series, where each term in the series is smaller than the last, because the fundamental coupling strength of electromagnetism is small, about 1/137. Adding up the first few terms gives a result extremely close to the full answer. For the strong force at low energies, meaning the energies relevant to protons and everyday matter, the coupling strength is close to 1. The series does not converge. Each successive term in the calculation is roughly as large as the one before. Adding them up gives nonsense. The standard calculation method breaks down completely in the regime that governs 99% of the matter in the universe. This is why quantum chromodynamics cannot yet prove confinement from first principles. Confinement is a low-energy phenomenon. The mathematical tools designed for the theory work at high energies, where asymptotic freedom makes the coupling small. At low energies, where quarks are trapped inside protons, the tools stop working. Physicists developed a workaround called lattice quantum chromodynamics. This method places space and time on a grid of discrete points and uses computers to calculate the strong force numerically across that grid. It is not an exact analytical solution. It is a computational approximation that can be made more accurate by using finer grids and faster computers. Lattice calculations have produced some of the most successful predictions in physics. The masses of the proton and neutron, calculated from quark masses and the strong force coupling alone, match the measured values with precision. The flux tube structure between quarks, the properties of exotic hadrons, the quark-gluon plasma transition temperature, all confirmed by lattice calculations compared against experiment. But the fact that the analytic approach to quantum chromodynamics breaks down at low energies means that physicists do not have a complete mathematical understanding of the theory they use to describe everyday matter. The calculations work, the predictions succeed, the underlying mathematical structure, from a rigorous proof standpoint, has a gap. That gap is precisely what the Clay Mathematics Institute targeted in 2000 when it listed 7 Millennium Prize problems. The Yang-Mills existence and mass gap problem asks for a rigorous mathematical proof that the theory behind quantum chromodynamics exists as a complete mathematical object and that it predicts a minimum energy gap in the force. Carrier spectrum. Nobody has provided that proof. The prize remains unclaimed. The physics works. The math is unfinished. This is one of the strangest positions in science. A theory that correctly predicts the mass of a proton to better than 1% precision, built on a mathematical foundation that has not yet been proven to exist in the way the calculations assume it does. In 2000, the Clay Mathematics Institute announced 7 problems. Each carried a prize of $1 million. Solutions had to meet strict mathematical standards, meaning complete rigorous proofs, no shortcuts, no numerical evidence alone. 6 of the problems were pure mathematics. One of them came from physics. The Yang-Mills existence and mass gap problem asks 2 connected questions. First, does the mathematical theory underlying quantum chromodynamics actually exist in a rigorous sense? Meaning, can it be defined precisely enough to satisfy the standards of pure mathematics? Second, does the theory predict that every particle carrying the strong force, every gluon state and bound state, has a minimum non-zero mass, a mass gap that separates the ground state from the vacuum? Physicists know the answers in practice. Experiments confirm the mass gap. Gluon states have non-zero mass. The theory's predictions match data. But a physical experiment is not a mathematical proof. The clay problem requires a proof that holds in the mathematical sense, independent of experimental confirmation. Nobody has produced one. The difficulty is fundamental. Quantum field theories are defined through a procedure called quantization, applied to classical field theories. For electromagnetism, this procedure is well understood and mathematically rigorous. For the Yang-Mills theory that underlies the strong force, the procedure works in calculations, but has not been proven to produce a mathematically consistent object in all cases. The low-energy behavior is the core problem. In the mathematical sense, a complete definition of the theory requires specifying what happens at all energy scales, including low energies where the standard perturbative calculations break down. At those scales, the theory must produce confinement and the mass gap, showing that it does not just numerically but analytically requires mathematical tools that do not yet exist. Physicists who work on this problem often describe it as requiring the invention of new mathematics, not the application of existing methods. The techniques used in perturbative quantum field theory, the standard tools of theoretical physics, are insufficient. Something new is needed. Several approaches have been attempted. One involves understanding the vacuum structure of the theory in detail. The quantum chromodynamics vacuum is not empty. It contains condensates of quarks and gluons, background fields that fill all of space, and affect how particles propagate. The vacuum structure drives confinement, but mapping it mathematically at the required level of rigor has not been achieved. Another approach uses a mathematical framework called topological field theory, studying aspects of the strong force that are insensitive to the specific energy scale. Some progress has been made. No complete solution has emerged. The prize remains available. The problem remains open. Every working physicist who uses quantum chromodynamics every day uses a theory they know works, built on a mathematical foundation that has not been fully established. And separately from the confinement problem, an equally uncomfortable question sits at the level of the quarks themselves. Why 6 flavors? Why those specific masses? Why those specific charges? The standard model takes all of these as given. No framework yet explains where they come from. 6 quarks. 3 generations. Each generation heavier than the last by amounts that follow no obvious pattern. The up quark is light. The top quark is roughly 85,000 times heavier. Between them, 4 other quarks fill in a mass spectrum that spans orders of magnitude, with no clear rule governing the spacing. The standard model accommodates all 6. It has slots for them. The theory works with 6 flavors and makes accurate predictions using their measured masses as inputs. It does not explain why there are 6, why the masses land where they do, or why generations exist as a concept at all. This is called the flavor problem, or sometimes the generation problem. It is one of the standard model's most persistent gaps. Particle physics is organized into 3 generations of matter. First generation contains up and down quarks, along with the electron and its neutrino. Second generation contains strange and charm quarks, along with the muon and its neutrino. Third generation contains bottom and top quarks, along with the tau particle and its neutrino. Each generation is a heavier, unstable copy of the one before it. The second and third generations decay into first generation particles. Nothing in nature around us is made of second or third generation matter. The heavier quarks appear only in cosmic ray impacts and accelerator collisions. So why does nature need them at all? One answer sometimes offered is that 3 generations are required for charge parity violation to occur in quark decays. With only 2 generations, the mathematical structure of the weak force does not permit the asymmetry between matter and antimatter that was measured in the 1960s. 3 generations allow it. If this connection is real, the existence of the 3-generation structure might trace back to the conditions needed for the universe to produce more matter than antimatter. But this answer raises its own question. Why 3 and not 4 or 5? More generations would also allow charge parity violation. The argument shows 3 is sufficient. It does not show 3 as necessary. Measurements of the Z boson decay at the Large Electron-Positron Collider at CERN in the 1990s placed a limit on the number of light neutrino types, constraining the number of standard model generations to 3. This is a measurement, not a derivation. It tells us there are 3 generations involving light neutrinos. It gives no theoretical reason why the universe stopped there. Some extensions of the Standard Model predict 4th-generation quarks with masses too large for current accelerators to produce. Others predict the 3-generation structure emerges from a deeper symmetry. None of these extensions has experimental support yet. The honest position is that physics does not know why there are 6 quarks, 3 generations, or why the mass ratios between them look the way they do. These numbers sit at the foundation of all matter and have no deeper derivation in any confirmed theory. Physicists have been looking for that derivation for 50 years. The search connects to every frontier of the field, including the relationship between quarks and the particle responsible for giving all of them their mass. Every quark has mass, and the origin of that mass involves a field that fills all of space. The Higgs field is not a particle. It is a field, meaning it exists everywhere in the universe simultaneously, the way the electromagnetic field exists everywhere. The Higgs boson, confirmed at the Large Hadron Collider in 2012, is the particle that gets knocked out of the Higgs field when you hit it with enough energy. The field itself was already there. Particles acquire mass by interacting with the Higgs field. A particle moving through space experiences a drag from the Higgs field, and that drag manifests as inertia, as mass. The stronger the interaction, the heavier the particle. For quarks, the interaction strength with the Higgs field is called the Yukawa coupling. Each quark's coupling is tiny. The top quark's coupling is close to 1, meaning maximum interaction. The other quarks fall somewhere between those extremes with no obvious pattern. The Standard Model does not predict Yukawa couplings. It takes them from experiment and inserts them. The model has no equation that says the top quark must interact with the Higgs field nearly 100,000 times more strongly than the up quark. It simply notes that it does and uses the number. Why the top quark couples so strongly to the Higgs field is unknown. Some physicists believe the top quark's special relationship with the Higgs points toward new physics. The coupling value close to 1 might indicate that the top quark plays a fundamental role in the Higgs mechanism itself, perhaps through loop corrections that affect the Higgs boson mass. This is part of an ongoing research area called top quark physics. The Higgs connection also enters the vacuum stability problem. The Higgs field has a potential energy landscape, and the universe sits at a specific low point in that landscape. Whether that low point is the true minimum, stable forever, or a local minimum that could in principle tunnel to a lower state, depends on the top quark mass and the Higgs boson mass. Current measurements place the universe in a metastable region. The vacuum appears stable on any timescale relevant to human experience, or even to the current age of the universe. But the possibility exists in principle. A small shift in the top quark's mass would move the calculation toward clear stability or clear instability. The measurement sits in the uncertain middle ground, and refining it is a priority of current accelerator programs. The Higgs connection shows that quarks are not isolated from the rest of particle physics. The same field responsible for all particle mass interacts with quarks at wildly varying strengths, producing the mass spectrum that the Standard Model records, but does not explain. Every quark mass feeds into the Higgs interaction picture, and the gap between the lightest and heaviest quark masses is the sharpest form of the question that the Standard Model leaves entirely open. What determines the masses? Why these numbers? What comes next when physics pushes deeper into that question? The most transformative scenario in particle physics would be discovering that quarks are composite, that there is a layer below, that the flavor problem and the mass hierarchy and the generation structure all emerge from something simpler underneath. Every major discovery in particle physics has forced a rewrite. The electron arrived in 1897 and made Thomson famous, the proton in 1919, the neutron in 1932. Each one required tearing out assumptions and rebuilding. The quark in 1964 did the same. Protons and neutrons stopped being fundamental. The periodic table of elements became a secondary structure built on top of a deeper one. A seventh quark would force a similar revision. The three-generation structure would be broken. The Standard Model, which has exactly 3 generations as a core feature, would need extension. Any theory that predicted a 4th generation would suddenly be live. Any theory that ruled it out would need explanation. Every equation that used 3 generations as an input would need to be reopened. Experimentally, a 7th quark would be the heaviest particle ever found by a large margin. It would require collision energies beyond anything currently operating. The Future Circular Collider, proposed at CERN as a successor to the Large Hadron Collider, with a tunnel roughly 4 times longer, would push into energy ranges where a 4th-generation quark might appear if it exists. The project is in planning stages. Physics is building toward the search. Discovering a preon would be more radical still. Quarks losing their fundamental status would be the biggest shift in particle physics since quarks themselves dethroned protons. The Standard Model would not just need extension, it would need replacement. The confirmed elementary particles, the objects that textbooks currently list as having no internal structure, would become composite. Every calculation that treated quarks as points would become an approximation valid only at low energies, the same way proton as solid sphere was an approximation before quarks. A preon discovery would also carry an immediate explanatory payoff. The flavor problem might dissolve. 6 quark flavors plus 6 lepton flavors might emerge naturally from the combinations of 2 or 3 preons, the same way dozens of hadrons emerge from 6 quarks. The generation structure might have a geometric or combinatorial explanation. The mass hierarchy might follow from binding energies at the preon scale. These payoffs make the discovery tempting to imagine. No experiment has found any signal. No deviation from point-like behavior has appeared at any energy tested. Either preons do not exist, or they exist at scales so small that reaching them requires energies vastly beyond anything humans have built. The energy required to probe below the current quark size limit is roughly 10,000 times what the Large Hadron Collider achieves. The physics community is not currently planning a machine at that scale. The search for preons, if it ever resumes in experimental form, lies decades in the future at minimum. For now, quarks remain fundamental in the practical sense. The Standard Model's 6 flavors remain the confirmed bottom layer. The unanswered questions about why those flavors exist and why their masses are what they are sit open, accumulating as each new experiment confirms the existing picture without illuminating what lies beneath it. What quarks have already taught physics goes far beyond particle classification. They have shown that matter has layers, that the intuitive picture of solidity is a construction, that the rules governing the smallest scales are completely unlike anything experienced at human scales, and that the further down you look, the more the universe refuses to behave the way common sense expects. The quark model is 60 years old. In that time, it has been confirmed beyond any reasonable doubt. Every prediction it made about particle structure has held up. The 6 flavors are real, the fractional charges are real, confinement is real. The strong forces behavior, from asymptotic freedom at high energies to the flux tube at low energies, matches calculations with precision that rivals any measurement in science. And yet the deepest questions remain open. Why 6 flavors? Unknown. Why those specific masses? Unknown. Why the universe produces slightly more matter than antimatter? Unknown. Whether quarks have internal structure? Unknown. Whether confinement can be proven rigorously from the mathematics of the theory? Unproven. The prize is unclaimed. This list should be uncomfortable. Quarks are the building blocks of everything you can see and touch. You are made of them. The planet under you is made of them. Every star you will ever see is made of them, and the rules that govern them contain gaps large enough that $1 million prize has sat uncollected for 25 years. This is what frontier science actually looks like. It is not a completed picture with a few details to fill in. It is a confirmed structure with foundations that remain partially unexplained. Physicists know how quarks behave to extraordinary precision. They do not know why the parameters of that behavior are what they are. The history of quarks also carries a lesson about how knowledge advances. Gell-Mann proposed quarks from patterns in data, not from a direct observation. The physics community rejected the idea for years. The Stanford experiments forced acceptance. Zweig, who independently found the same model, was dismissed by journals and lost years of recognition. The truth of the quark arrived through a combination of mathematical insight, experimental courage, and the willingness to accept strange answers when the data demanded them. Every layer of physics has followed that path. Atoms seemed final, then protons, then quarks. Each time the universe turned out to be more intricate than the previous layer suggested. Nothing in physics has ever indicated that any given level is the last one. Quarks behave as points. At every energy scale tested, they show no substructure. That might mean they are truly fundamental, or it might mean the next layer requires energies that humans have not yet reached. The question is not answerable with current tools. What quarks have already given us is a picture of matter at its deepest confirmed level, a picture full of confirmed strangeness, force fields that gain strength with distance, particles whose mass comes mostly from the energy of other massless particles, building blocks that cannot exist alone, a universe that responds to attempts at isolation by creating more matter, a stability built on violent internal chaos. The smallest confirmed things in nature carry the largest unresolved questions in science, and the pattern that quarks fit into, the one that is repeated every time physics reached a new depth, suggests that the story does not end here. The next layer, if it exists, will be stranger still. The questions quarks leave open are not loose ends. They are the outline of a door that no machine built yet has been able to open. The universe keeps its deepest answers locked behind energies humans are only beginning to reach. And it has never, in the entire history of science, turned out to be simpler on the inside than it looked from the outside.